Hi, I'm Carrie Laboski, a professor and soil fertility specialist at University of Wisconsin-Madison. Today I'm going to present on the relative importance of phosphorus and potassium for corn and soybean production in Wisconsin. Now, we're going to start off looking at two case studies, and the first one is an example of a soybean field where you can see there's in the photo some better looking areas and poor looking areas. Close-ups, I don't have a close-up photo of the field, but the close-ups do indicate potassium deficiency where there's necrosis on the leaf margins. What also shows up in this field is that the field is sort of divided in half. The right side of the field doesn't look quite as bad as the left side. It's a little more green, but there's some striping in there. The field history of this is that the previous growing season it was all in corn, and the field was harvested for grain on the right side of the field and for silage on the left side of the field. And this makes some sense when we look at the condition of the soybean crop, because grain production, when we harvest that, we've got a lot of the residue is left on the soil surface, and potassium leaches fairly readily out of crop residue. So we had some return of potassium from the corn that had been taken up by the corn to the soil, and the soybean crop is not looking as deficient. On the left side, where we had silage taken off, there's no crop residue left, so to speak, and there's a lot of potassium removed, and we're seeing greater deficiency. What also shows up in this field is this striping effect, where you can see it's a little bit greener and then it gets yellow in places. And those yellow stripes, or I should say the green areas, are more on 30-inch centers. And they align with the corn planter from the previous year where starter fertilizer had been used. Now, the Mike Ballwig, who had taken these photos, he had also done some soil sampling at the base of the plants that were green and at the base of the plants that exhibited potassium deficiency symptoms. And what he found is there was a 5 part per million difference in soil test K levels between those two areas. And so in the area where starter fertilizer had been applied, soil test K was 60 parts per million, and between the rows where there was no starter fertilizer for corn the previous year, the soil test was 55. So while neither of those soil test levels is very good for soybean production, you can see that there's sort of a bit of a cliff there when it looks to the visual symptoms of deficiency. And I'm sure that we're still seeing a bit of a yield reduction even at the 60 part per million soil test K level. Now, moving on to the second case study, I just wanted to show what advanced potassium deficiency looks like in corn. And here is a photo standing in the field. Early to mid-September is when the photo was taken. The corn looks really tough. It's short, spindly, a lot of dead tissue there. One plant was dug out, and you could see it laying on the ground here. It does have an ear, but it's not very big. In the soil tests, there was a sample taken in early August of that same year, and it was 42 parts per million, so that's very low. I'd like to point out that these two fields, we have some very low soil test levels, and these are not, this type of soil test level does not just happen overnight. You don't go from being optimum down to 42 part per million in one growing season. It's happening over time by the failure to apply potassium. So that sets the backdrop for discussion of some research that I conducted at our Arlington Ag Research Station looking at the response of corn and soybean to P and K. Now, we had two sites. They're actually in the same field, but they are started in different years. Site A was established in 2011, and the initial soil test P was 8 part per million, and potassium was 59 parts per million, so very low. Site B, in the same field but a different part of that field, was established in 2012. Here the soil test P was even lower at 1 part per million, and soil test K also was lower at 48 parts per million. Now, this field had been no-till for a number of years. The previous crop was alfalfa. So we decided to keep the study no-till, and we have treatments where we had 5 rates of potassium broadcast from 0 to 160 pounds, and then 4 rates of P from 0 to 90 pounds. And so all combinations of P and K were applied. They were applied in the spring of every year, and once a treatment was assigned to a plot, it always received that same treatment. Now, we did establish the rotation in each year with soybean. So we didn't start out in year one with both soybean and corn. It was just soybean only. And then in 2012, we started the new site with soybean, and that site B with soybean, and then site A became corn. And here you can see just what some of the corn looked like this past growing season. We have a lot of K deficiency showing up in places, and you could also see we had Bucky Badger in our plots. Not too often you get to get a close-up of a badger right in the middle of your plot. So moving on to some of our results. Here we have soybean yields from 2011 through 2014. And we're looking at the relationship with potash application, so from 0 to 160 pounds of K2O. And then we have our grain yield. And you can see we have a nice yield increase in all years. And even in 2012, the drought year, we had a steady increase in yield. And when we look at this overall, from where no K was applied, we saw a 50 to 75% yield increase in applying K on these low K testing soils. So that's a pretty big yield increase. Now I also want to point out at the bottom our soil test levels. Here in blue marks the initial soil test levels at this site before we put any treatments on. And then within the green, this is what the soil test levels were after 2 years of application. So you can see that when 160 pounds of K was applied for 2 years consecutively, we were able to increase soil test K from in the mid to upper 50s into the 80s. So you can see how much we can build soil test K. So now we're going to look more closely at 2014 data for both P and K with regard to yield. Here in this table we have our rate of K application, 0 to 160 pounds, and our rate of P application, 0 to 90 pounds. On the bottom we have our mean. And what this is it's the yield obtained when 0K was applied, averaged over all of the P rates. And here, to demonstrate further, where 160 pounds was K was applied, averaged over all P rates, 56 bushels was obtained. Now, you see some letters behind the numbers, and the letters indicate statistical significance. So yields with the same level or letter are not different from each other, and where you have a different letter, that means those yields are statistically different from each other. So this is showing, once again, that we had a very nice response to K application. Now, if we look at this mean column on the right, this is showing our response to phosphorus. And so this says that we got 48 bushels of corn when no P was applied, and that's the average over all rates of K. And when we applied 90 pounds of P, we got 50 bushels. So there's no response to P, even though those initial soil test P levels were less than 8 parts per million. I do want to point out that the study is still ongoing, and we'll see where the additional research takes us. Now I also want to show here, this is a nice visual of what this looks like. And so these photos were taken in August of 2014. We have in the top left, no P and no K was applied. You can see a lot of K deficiency showing up. The beans did not close the row. They were planted in 30-inch rows. Here we have 90 pounds of P and no K. Doesn't really look any different than no P, no K. A lot of K deficiency showing up, small beans. We move down here to the bottom left, no P but 160 pounds of K. Plants are looking much better. We see no deficiency symptoms for K. They're pretty much closing the row. And then where we have 90 pounds of P and 160 pounds of K, they don't really look that much different than when there was no P from across here. So that's just how it looked, and you saw what the yields were. So now moving on to our corn yield. Here we have a similar graph to what we had with soybean. We have our K response, where our K application rate is on the bottom and our corn grain yield is on the side. We have the 3 years from 2012 through 2014. We can see we have very nice yield responses. 2012, the drought year, is in blue, and that shows up where we had substantially reduced yields, but we still had a strong K response. Now, what strikes me the most about this graph is actually the yield at 0K. Here we're looking at 40 to 50 bushels grain where we did not apply K on low K testing soils. What is so interesting about this, on these same soils at this research station, if I was conducting a nitrogen rate study and we didn't put any nitrogen on, but the soil test P and K were optimum, I would be getting 100, 120, maybe even close to 150 bushels of corn with no N. And so it's amazing that if we have low K and we don't put K on, we have a much greater yield suppression than what we do without putting nitrogen on if our P and K are adequate. That is really amazing. And so we look at our yield increases as percentages. We saw 150% yield increase in that drought year, but in the other 2 years, it was up to a 560% yield increase. So substantial yield increases by applying K when it's needed. And again, I just want to point out soil test levels. This first couple rows in blue shows the soil test level after 1 year of application, and in green it's after 3 consecutive years. So you can see that where 160 pounds of K was applied 3 consecutive years, we had soil test levels of 91 pounds, or 91 parts per million. So let's look a little bit further at our response to both P and K in 2014, set up the same way as the soybean table. And so if we just start on the bottom, looking at our response to K, the average yield for each rate of K applied, and that's averaged over all rates of P applied, we can see a very nice increase in response to K application. Now, if we look at the column here that represents our P response, if we do not apply any P, the average yield over all rates of K applied was 155 bushels. But as we increase the P application rate, we increase yield all the way up to 170 bushels. And you can see we now have letters here indicating that we have statistical significance, so that we're getting a nice yield increase to P application. I think we need to dig a little bit deeper into this table as well, because when we look at where 0 and 40 pounds of K was applied, and then look at all the yields at all rates of P, we don't see a lot going on. So for example, where 40 pounds of K was applied and no P, the yield was 156 bushels. If you applied 90 pounds of P, you only got 157 bushels, so no response. But if we bumped up to 80 pounds of K applied annually, our yield now at 0 pounds of P jumps up to 194 bushels, and you can see where we put 30 pounds of P on, we have a nice yield increase of 215 bushels, and then a further increase up to 230 bushels where 60 pounds is applied. Now, if we were to look at the 120 pound application rate, for K, we can see again another strong response to phosphorus, and here yields increasing all the way up to 243 bushels. So what this is indicating is the concept of one nutrient can be more limiting than another nutrient. And in this case, potassium is much more limiting than phosphorus. And once we remove our potassium limitation by building the soil test levels up and continuing to apply K, now we can get a response to additional P application. But if we don't do anything with the K and the soil test levels remain low and we don't apply any K, we're not going to get any response out of phosphorus. So that says any money that we would have put into phosphorus here is really kind of wasted, that you need to have both going and have much higher soil test K level before you'd see a response to P. And when we look at the data and analyze it more thoroughly, we find that if annually we've been applying 80 pounds of K2O per acre per year, then the agronomic optimum P rate was 50 pounds per acre. If we're looking at our agronomic optimum K rate, then that was 92 pounds. So you can see that it's really interesting, demonstrating the need that potassium is probably much more limiting in our production systems for corn than phosphorus. Now with soybean, we didn't see any response to P. Like I said, we're continuing the study more, and I'm curious to find if we need to build soil test K levels up to an even greater point for soybean before we start seeing any responses to P. Now, before we move on, I did just want to point out, as I've been with where soil test levels move over time, and here, after 3 consecutive applications of phosphorus, we can see that we've built soil test P up from 8 part per million all the way up to 22. So you can build P relatively quickly if you need to in those type of situations. So again, just want to summarize that both P and K are important for corn and soybean production, but K is probably much more important, especially if soil test K levels are low. Do not skimp on potash. You really need to apply that fertilizer, and often I think many people think that phosphorus is much more important to K only because a bag of fertilizer is NPK, on our analysis. And that's just the order it is. It doesn't necessarily mean it's more important. So keep K in mind and really think hard about where you're going to be spending your fertilizer dollar this year. If you have any additional questions, this is where you can contact me.